After sintered and polished, several advanced ceramics are presented here, which can be used in any different areas. We can see their shape, their size, and their colors with our naked eyes. But most important features, which decided the properties and performance of the advanced ceramics, the microstructure, can't be seen directly. In this video, we are going to discover the world underneath the surface of the advanced ceramics and find out the connection between the properties and the microstructures. First, let's focus on the microstructure of ceramic materials. We will see the grains and grain boundaries in the ceramics. In some special applications, single crystals of ceramic material are prepared and used. That will be not discussed here. Because most of ceramics are polycrystalline ceramics, microstructure of ceramics, which is too small to be seen with the naked eye. But it plays an important factor in the final property of the materials. From the ceramic microstructure schematic diagram, we can see that the microstructure is made up of small crystals in a typical ceramics. A crystalline face is called a grain. Glassy face surrounds crystalline face is called a grain boundary, and there are many pores inside ceramics. The quantity, shape, size, and their distribution of each face determine the properties of ceramics. We will introduce each face in detail below. For sintered ceramics, the average grain size distribution are important. Typically, ceramics with small grain size are stronger than the coarse-grained ceramics. From this figure, we can see that the normal strength of small grain size ceramics is about 150 MPa higher than that of big grain size ceramics. The reason is that finer grain size help minimize strains that develop at grain boundaries due to anisotropic expansion and contraction. So, what factors affect ceramic grain size? Here, we give three main factors. Normally, starting with thinner ceramic raw materials produces a thin grain size. The other reason is sintering conditions. It has been mentioned before that changes in the sintering conditions can change ceramic grain size. If the sintering temperature is too high or the holding time is too long, it will cause the growth of the ceramic grain size. On the other hand, the change of composition in the raw material of the ceramics also causes the change of grain size of ceramics. This is Zhao's research work we see before. We can see the little change of the composition. The difference of grain size is obviously, although they were centered in the same condition, except the mechanical property of ceramics are affected by the grain size of ceramics. Magnetic, dielectric, and optical properties of ceramic materials are also dependent on the average grain size. Therefore, grain size, both structural ceramics and functional ceramics, must be controlled for their applications. Just like in every material, the properties of ceramics are determined by the tips of atoms present, the tips of bonding between the atoms, and the way the atoms are packed together. The tips of crystalline face or the macrocrystalline face in advanced engineering ceramics determines the key property of the ceramics. Commonly, crystalline face in engineered ceramics include, for example, alumina, zirconia, silicon carbide, silicon nitride, boron nitride, and so on. What are the crystal structure of ceramics? The answer to this question can explain why ceramics materials have high elastic modulus and higher hardness and high melting point. Depending on the tips of atom bonding in the crystalline phase, the ceramic can be roughly divided into ionic bonds, covalent bonds, and mixed bonds composed of ionic bonds and covalent bonds. For each type of atom bonding, we will give an example of its crystal structure. The showing crystal structure is alpha alumina. In alumina, the oxygen anions packed in a hexagonal arrangement, and the aluminum cations occupy some of the available octahedral position. The oxygen and aluminum bond has an ionic character. Ionic bond is found in many other ceramic structures, such as zirconium, magnesium oxide, and sodium chloride. Covalent bond is found in many ceramic structures, such as silicon carbide, diamond, silicon nitride. The atoms in these ceramics are arranged so that each pair of nearest neighbor atoms forms a chemical bond by sharing a pair of electrons. The next example is the covalent bonding of silicon carbide. It's a simple compound with a carbon atom attached to the silicon through a triple bond. The bonding between them has a covalent character. Actually, in many bulk ceramic materials, covalent bonds and ionic bonds are coexisted. In most commonly silicates, each silicon atom occupies the center of an idealized tetrahedron, whose corners are 4 oxygen atoms connected to it by single covalent bonds. However, a silicon-oxygen tetrahedron is an ionic group. The tetrahedron linked to form a chain by ionic bonds. So silicates has a mixture of covalent bonds and ionic bonds. The ionic and covalent bonds of ceramics are responsible for many unique properties of these materials, such as high hardness, high melting points, low thermal expansion, and good chemical resistance. From this table, we can see the relation between bond energy and melting point of some ceramics. That shows higher bond energy, both for ionic or covalent bond, lead to a higher melting point, but also for many undesirable characters, foremost being brittleness, which leads to fractures unless the material is toughened by reinforcement agents or by other means. Another phenomenon is that the crystal face of ceramics has polymorphism. That means the existence of a crystalline ceramics in more than one form or crystal structure. Many crystalline ceramics exhibit polymorphism, such as alumina, zirconia, silicon carbide, and silicon nitride. The table shows the difference of crystal structure in several common ceramics. Here we can see the pure zirconia has 3 different crystal structures. With change in temperature, the crystal structure of zirconia can be monoclinic, tetrahedral, or cubic. When zirconia changes from tetrahedral to monoclinic phase, there will be increase in volume leading to high tension in the ceramics. That means the polymorphism phenomenon influences some property of ceramics absolutely. The above discussed crystal structures are in the ideal crystalline state. However, ceramics also have crystal defects. Pot defects is one most common type of crystalline defects in ceramics materials. In this figure, we see there are 2 vacant sites existed in the solid solution of alumina in magnesium oxide. A great many properties of crystals are determined by imperfects. Electronic conductivities and diffusional transports in most ceramics is determined by the number and type of defects. Various optical properties, for instance, those giving rise to color and laser activities, are caused by electronic absorption and emission process, and impurity ions and point defects. The rates of kinetic processes, such as precipitation, densification, grain coarsening, and high-temperature creep deformation are determined also by mass transport due to defects. Although it can accelerate the diffusion of atoms in the sintering process of ceramics and improve the sintering rate, it will also reduce the property of the ceramics materials. In some cases, there is more than one crystalline phase in ceramics. The one with more contents is called the main crystalline phase. The showing figure is the microstructure of zirconium tufted alumina ceramics. The green grain is alumina and the white grain is zirconium. Obviously, the alumina is the main crystalline phase in this kind of ceramics. The main phase and the second phase are all important factors influence the property of the ceramics if they optimized prepared. Back to this diagram, we see the grains are separated by grain boundary, right? In many instances, grain boundary is glassy phase. In case of a glass material, the microstructure is non-crystalline. Glassy phase is formed during cooling and the solidification of the liquid phase formed by a series of physical and chemical reactions between each component's phase and impurities during sintering of the ceramics. When those two materials are combined, I mean the glassy phase and the crystalline phase, the glassy phase usually surrounds small crystals, bonding them together. A microstructure change during a solid phase sintering can be explained by this diagram. During heating, the solid grains center a metal forms. It causes the solid grain to rearrange. With solution and reprecipitation of glassy phase, the densification occurs. At the same time, porosity decreases as grain shape change. The glassy phase can fill grain gap, bond the grain, reduce porosity, and improve density. It can also reduce sintering temperature, increase sintering process, and decrease grain growing. However, depending on the application, the content of glassy phase and grain boundary also should be considered. Usually, the glass phase has low melting point. It's a poor thermal stability that will severely affect the property of ceramics when it is used at high temperature. And the glassy phase can also reduce the insulation of ceramics. Again, we review this diagram and focus on the pore in the ceramics this time. Let's see the real pore in a typical ceramic. The showing figure are the microstructure of silicon carbide ceramic, prepared under different conditions. The pore exists in both samples, obviously. At the same time, we can see the porosity of each sample is different. It necessarily generates porosity by fixing in 3 dimensions positions and relations of interparticle voids. This model explains pore formation during the sintering process. One thing to be clear, we see the loss of pore volume or porosity must be accompanied by shrinkage of the piece grain body. Usually, pores represent the most important defects in polycrystalline ceramics. The presence of pores is usually harmful to the mechanical property of bulk ceramics, since pores provide a pre-existing location for which a crack can grow. As a result, most ceramics shows such brittle behavior under tensile loading. From these figures, we see that the flexural strength and the modulus of the elasticity decrease with the porosity increasing. The porosity in the ceramics depends on several facts. Low pressure forming methods generate higher porosity, and higher pressures produce less. Therefore, hot pressing sintering is used to eliminate some, most, or all porosity depending on end use. The size of pores depends on the particle size distribution and the shape of the starting powders and various additives, such as binders and liquids. We should know that the additives create porosity in the initial stage of firing or sintering due to their loss or burning out. Porous property impact on ceramic both positive and negative. In the right hands, in the right product, porosity is very useful. It can increase resistance to heat conduction and thermal shock. And high porosity can also reduce the density of the ceramics. For lubricating materials, pores provide a storage of lubricating media. In certain applications, such as filters for hot metals or for liquids or gases, the presence of interconnected pores is desirable. This figure shows porous ceramic materials used as catalyst carriers. So far, we have finished describing the feature of the microstructure of advanced ceramics. And for the greater property of these materials given by the microstructure will be presented in our next video.